Helen here. I'm a NERSC high-performance computing consultant. We help scientists to run our facilities. So this is my outline. I'm going to introduce what is NERSC and what is our new system. Outline, I'm going to talk about what is NERSC and our new system, Cori, and why MPI plus OpenMP is preferred. I'm going to tell you about how the basics, how much OpenMP is used at NERSC, and then what we tell our users about OpenMP scaling, and how it's process and stress thread affinity, how important are they, some scaling tips, and what are tools we have for OpenMP. Then I'll present a few case studies of tuning and optimizing the performance on hybrid MPI OpenMP. So NERSC. So what is NERSC and /LBNL? If I have to say just one sentence, what is NERSC? NERSC is the primary computing facility for Department of Energy, Office of Science. And we support about 7,000 users, 850 projects, and 600 codes. On the right side, the allocation breakdown shows 6 program offices from DOE. We emphasize a lot of science. We promote science, help scientists to run, and we have lots of journal publications, and we have 4 Nobel Prize winners from our users. And yesterday at the panel, people asked whether we collaborate with vendors, and yes, we do. We have always actively talking to vendors, even years before a system is arrived. We have lots of first kind of system at NERSC. NERSC, we use NERSC 6, 7, and 8 as our procurement. So NERSC 6 is Hopper. It is the first Cray petascale system with a Gemini interconnect. And NERSC 7 Edison is the first petascale system with Intel processors, Aries interconnect, and Dragonfly with Dragonfly topology. NERSC 8 Cori will be one of the first and largest KNL systems that have its unique data features. The Cori phase 1 with Haswell has already arrived. We do lots of configuration right now. Cori phase 2 will be arriving next year. And sometimes people are confused why you're sometimes NERSC, sometimes LBNL. So LBNL is our organization, Lawrence Berkeley National Lab. NERSC as a computing facility is a division in the lab. It is one of the 3 divisions of the computer science area. The big picture is that Cori is coming. It's energy efficient mini core system, has over 9,300 single socket nodes. It will have multiple NUMA domains. We always consider about NUMA domains for affinity, things like that. It will be self-hosted, not an accelerator. And it will have a total of 288 logical threads with 72 cores per node and 4 hardware threads. It also has AVX512, very large vector length of 512 bits, equivalent of 8 double precision elements. It'll have on-package high bandwidth memory and burst buffer for fast I/O. So this is a quick comparison with Edison. We have now is Ivy Bridge Cray XC30 system versus Cori, the Knights Landing. So the number of cores per CPU will increase significantly, and per core CPU is slower. The vector length will be doubled from 256 to 512, and memory per core slow memory is about the same, but then the fast memory will have on-node smaller per core fast memory, which has 5 times DDR4 bandwidth, and also has a burst buffer. So some programming considerations to running on Cori. It's probably, if you port to a very simple porting, your application is likely to run, but with pure MPI, it probably won't fit in the memory, and you would have to explore on-node parallelism. Because if you want to run pure MPI with so many tasks per node, it has lots of overhead. So you want to use on-node parallelism with either with both thread scaling with OpenMP or and vectorization. to explore the SIMDI, not explore the larger vector lengths. And then for Cori, you also would like to explore high bandwidth memory and burst buffer options. So we recommend hybrid MPI OpenMP for both scaling capability and for code portability. We have the current system, the Edison Hopper, our Cray systems, and the Babbage is our Intel Xeon Phi nice corner test bed. So we ask users can now prepare codes for Cori on these systems. One slide about portability and maintainability. Many of our users are also users at other DOE labs. Regardless of their different architectures, users would have to modify their codes to achieve performance. They would always want to expose more on-node parallelism. OpenMP threading can help, and to increase vectorization capabilities, OpenMP SIMDI can help. That's why we want to promote OpenMP as an industry standard for portability. And it's like Tim mentioned, portability is sort of a hard to achieve goal, but the real goal is programming maintainability. You would like to have a single source for your application and to reduce as much as possible for those if-defs, whether if-def GPU, CPU, if-def different compilers, if-def OpenACC, OpenMP, CUDA 4chan, or things like that. So, and I want to talk about application readiness for Cori. NERSC has already begun to transition our workload to the Cori system. However, as I mentioned, we have over 600 projects. It's impossible to hand-holding every one of them. So we have, the right side is our breakdown of the application. Basically, top 10 codes would make up about 45% of our workload, and 25% codes would make up 66% of workload. So what we did is we chose 20 applications, and as tier 1 and tier 2, we have about 30 more tier 3 with access. With tier 1 and tier 2 teams, we work with them very closely with Cray, Intel, and we have NERSC team together to look intensively at the code optimization. And with these 3 levels of code, on the right side, you can see the green and light green, which covers a lot of percentage of the NERSC workload. Some of them are as proxies. We also collaborate with other DOE centers, and we would distribute our lessons learned to the communities. So the next section I want to talk about is the OpenMP usage at NERSC. Some of slides James already showed yesterday. The first slide about languages used at NERSC. So again, I basically want to emphasize to this OpenMP community that please don't forget about Fortran users. Because of the legacy of science applications, many of these application codes are like millions of lines or 500,000 lines. So it's hard to convert from Fortran to C. They're just there. And if we, from this one, the data in this plot is collected from all NERSC projects, but we just choose by, if we count by machine hours used, then even about 2/3 of top codes primarily use Fortran. Some communities even just the 100% Fortran, like climate that I know of. About programming models, basically MPI still dominates, and 40% of projects use OpenMP so far. This is about number of projects, not about hours, and I'll show data about machine hours usage and the percentage of hours used at OpenMP, with OpenMP. And this is an answer about if you use MPI plus X, what is X? So OpenMP is about 50% of that X, and CUDA 4chan, OpenACC, it's kind of still on the top-ish, besides P-threads. It was because we had a GPU test bed for a while, and I think users explore these options. We also have TBB and Silk users, a small percentage. We get tickets from them sometimes. Okay, so this is a breakdown of with fraction of MPP hours and how much of OpenMP is used. It's about 20% on Edison. Edison is our newer system, and it's increasing over the years compared with Hopper, for example. So you can see different number of threads. From Hopper to Edison, you can see that number of threads used is higher because the number of cores available within one NUMA domain. And people use OpenMP not because they don't have enough memory. I think OpenMP especially helps you to scale to higher core counts. That's one of the main reasons for the current system. But for Cori, it's also because you want to explore more unknown parallelism. So this slide shows basically the number of threads used versus the job size. The bigger the job size, people use more threads. This is also one of the reasons because of the reason I mentioned. Only when you explore more with OpenMP add-on to pure MPI, you're able to run full capacity of the system. And also, I didn't show here on the slides, the job size over 64K. Even 2/3 of those jobs use OpenMP. Okay. So this is an interesting story, interesting slide so different science areas are adopting OpenMP very differently. Some of on the right side of the slides, you can see these areas almost not a pure MPI yet. And so one of the best using science areas are astrophysics and fusion. And number of threads they use is 12. And there's one bioscience, you can see their number of slides used is 24. It looks like they're doing lots of you can see embarrassingly, in OpenMP, not embarrassingly MPI. They use treat each thread separate, individually doing their work. There's also an area fusion, what is that? No, nuclear physics. They use number of threads as 48, turning on hyperthreading on Intel, on Edison. Okay. So next section, I want to tell you what we tell our users about OpenMP scaling or some tricks and things. I won't be able to cover everything we tell users, but pick some things I think are important. The first one is why scaling are important. So this is a slide from James Ryder's book. For a smaller number of threads, Xeon would win, but then slowly Xeon 5 will catch up. Like James showed yesterday, if you do 8 times 16 single precision from vectorization when times 240 threads, it's over 3,000. But then here we are from this scaling plot, we are not actually, we know scaling is important on the node, but we're not trying to scale our users. You have to use 200 all the way to 240 threads. You have to scale perfectly with that, or you have to use 240 MPI tasks to scale perfectly. Basically, we would tell users, try hybrid MPI OpenMP and find a sweet spot. It's probably between, say, 4 to 15 MPI tasks times 8 to 20 threads, something like that. So what we ask users is always do your OpenMP scaling study. And so it would depend on the problem size, of course. And you fix the number of MPI, and you find out how OpenMP scaling starts to fall down. And then this is basically the optimal number of threads we'd like to use. So the next one we want to do is OpenMP versus MPI versus OpenMP scaling analysis. So this plot is kind of hard to read. Let me try to explain. You see 4 lines here. Let's try to focus on the first line, purple. This is basically a line of, say, you fix total number of MPI times OpenMP threads. So this purple line total number is 60. The first dot is, say, you use 60 MPI tasks times 1 thread. And the second one is 30 MPI tasks times 2 threads. And then you do the same for all different way, 120, 180, and 240. So then you see where is your sweet spot. In this plot, you would see sweet spot is about the red line at the bottom at 15 MPI tasks. And then this line is 240 way total. So you know this is, this line is 120 way total. So now you know your sweet spot is 15 MPI tasks times 8 OpenMP threads. The sweet spots, again, still depend on your problem size and your algorithms. But this is a good guideline to start from optimizing and always compare back with your results.
Is this different for Xeon versus Xeon 5?
No, this whole study is on the Xeon 5. Okay. This study, case one. Okay, so the next few slides I want to emphasize on process and thread affinity, the importance of those. So first, let me introduce systems and basically a schematic plot of NUMA domain and yeah, basically the core, the node and the NUMA domain. So for the left side is our Hopper, is the Cray XE6. It has 4 NUMA domains per node and 6 cores per NUMA domain. And on the right side is our Edison, the Cray XC30 system. It has 2 NUMA domains per node, 12 cores per domain, and it also has 2 hardware threads per core. So this is what we get. This slide is about some of the options, how you try to make sure your MPI, distribute MPI rank evenly onto different NUMA nodes. How important is that? So this, and how to use some kind of a runtime control to achieve that. So AP run is sort of MPI equivalent to run on our Cray system. There's an option called -S, which is MPI tasks per NUMA domain. And the plot on the right shows a GTC performance with and without distributing your process MPI tasks onto different NUMA domain. And so the blue and yellow, you can see that with different number of MPI tasks times OpenMP threads, with and without, always when you distribute, it's a win. But then also in this plot, it also helps. I also demonstrate the sweet spot choice in it. Now get down to the thread affinity. After process affinity, you want to make sure your threads are close to wherever your MPI tasks are, and as close as possible. So the default for the AP run option is -CC. It basically binds your thread to a specific core within a NUMA node. So it's good for other compilers. Basically, we have Cray compiler, PGI compiler, and GNU compiler, and Intel. So every compiler except Intel, -CC CPU is great. It always binds you to the direct core. With the Intel compiler, it does have basically a thread manager. A manager thread. So if you do that, then when that manager thread is busy working on managing, and then the work assigned to this thread for OpenMP work will be blocked. So what we tell users is, please don't use that. If you have, you want to use one MPI only on your node, use -CC num, basically allow your OpenMP thread to migrate within the node. And if you have, say, one MPI task per NUMA node, then you would allow your threads to migrate within your NUMA node. You would use -CC NUMA node. And there was also a Cray improvement. If you have multiple MPI within a NUMA node, there's a smaller confinement. You can allow your thread to migrate freely, which you can use with -CC depths. So this is a slide about the KNC testbed. So for this testbed, we have 45 nodes, and on each host node, we have 2 mic cards. And so up to 200, on each mic card, we have 60 cores times 4 hardware threads. Since we know what the cores look like before we get this KNC testbed, so because Cray is going to be self-hosted, and what we tell users is that on Babbage, when you try to use Babbage to prepare for query, use the native mode only. Native mode means you run directly on the mic without worrying about inter-node communication, without worrying about host-to-node communication, things like that. So even though the symmetric, offload, all these modes work, OpenMP target work, everything works, but for the recommended model on this machine is just native and try to focus on single node optimization. So this is an illustration of the Babbage Card mic card. So you treat it as one single NUMA domain, and these, how many cores there are. So there are Intel-specific environment variables to control Affinity. There's also, we can tell users you can use OMP proc bind to do the thread control. There's also the MPI ping domain for MPI/OpenMP process and Affinity control for that. I'm not going to show details, but there are ways to manage. So I talked about thread process and thread affinity. Now it's the memory affinity. So we tell users about first touch means the memory is assignment, which memory is assigned to. That's the array this thread is working on based on when you initialize it, not when you allocate it. So we tell users you can try to create another initialization section with the exact same scheduling and number of threads. You get that. So the plot here shows with and without. And if you on this hopper, you have six threads per NUMA domain. So once it's over 6, if your memory is in the far NUMA domain, your performance suffers. So this is so hard, very hard for real application to do all these. So what we tell users is basically, please use less than 6 threads on our hopper machine, and then use 4 MPI tasks. It's an easy way to achieve equivalent performance. And we also try to, promote nested OpenMP. More and more applications are trying to do this now. And this slide basically shows how to achieve that. And you want to set OpenMP nested true. However, you do get number of threads in each level, but it's more important to get the best process affinity get the best process affinity binding with nested OpenMP so that performance will not suffer. But it's not very straightforward to do so. And it also, there's varying factors about what compiler you use, what batch schedulers you use, and there's a flags with runtime control, and also different systems. And different compilers I mentioned, like Intel has the different manager thread. And with on Torque and Moab on our Cray system, we use AP run. And we're now going to transition to Slurm. So it's going to be SRun, and so all the flags are going to be different. And our different systems, and I'm talking about Cray systems and Intel KNC, so it's all different factors together. And it's hard to achieve. But this is a sample settings. But then I put together a web page on nested OpenMP with detailed examples, and there's a sample code from Cray, basically prints out the thread affinity, so helps users to check whether they get their desired binding. Okay, OpenMP4 SIMDI. This is a slide from my colleague Jack. He says, a year ago, to get a vector code, you have to use intrinsics, and you pray the compiler would choose to vectorize the loop, or you have to use Cray compiler-specific directives. Today, you have the SIMDI option to use that. And of course, because SIMDI, you force compiler to vectorize for you, it bypassed compiler analysis, so you might get some incorrect results because you tell users there's no dependency there, just vectorize it. And here is the SIMDI you can do OMP do SIMDI. For the do, you would do distribute work among threads, and then for the SIMD, you would distribute the work onto further to fit into the SIMD vector register to do that. And I personally liked OMP declare SIMD because it tells a compiler to generate a SIMD function. We have a use case for that. We have elemental function, and the compiler, it's very hard for compiler to vectorize it. So I'm going to show that later. We use that feature. And a few slides, a slide about adding OpenMP. So we recommend users to use a Cray review tool, which is a part of the Cray Perf Tools package, and it does scope analysis and based on performance state analysis, performance analysis plus the compiler, the loop mark listing analysis and optimizing vectorization results. Combined together, it does suggest to you the OpenMP directives to add. Sometimes it'll tell you I have unresolved variables. I don't know whether it's shared or private, but users would go back and change those. It doesn't do many fancy things. It doesn't do reduction, things like that. But it does a basic loop level, and it can start from like topmost hot regions, and then users can do this incrementally. So that's it. You have to do it on Cray compiler first, but then the generated, OpenMPmized code can be used to use other compilers to run with it. And on the KNC, the Intel Advisor tool basically helps you to guide which threading options are good, whether you want to use OpenMP or TBB, things like that, give you some guidance. And this is the list of the performance and debugging tools available on our systems. Basically, we have vTune on both our systems, and we're promoting vTune a lot right now. And performance-wise, we have a linear map on both systems, and Cray tools on Cray systems, and Intel tools on Intel system. And debugging, we use DDT and TotalView mostly. And next few slides are basic general programming tips. We tell users how to add your OpenMP. We tell users, based on your algorithm, what's easier, and you might want to decide whether you want fine-grained or coarse-grained parallel implementation. And we tell users, add OpenMP incrementally. Use your tools to find hotspot first. And to parallelize outer loop, and if you can collapse some loops, minimize shared variables, minimize barriers, and decide. The last two are harder to do: overlap, MPI communication, and computation, and consider OpenMP tasking.
How do you check correctness?
How do I check correctness? I think compare with your sequential code first, or MPI code. Yeah. There's tools, like I mentioned in the previous slide, like Intel Inspector and DDT TotalView. That also helps to check OpenMP code. Okay. So users might ask why sometimes my MPI OpenMP code is slower than pure MPI. Maybe you have a serial section was not parallelized. Maybe you run into the force sharing situation, and there's always thread creation overhead. And then NUMA effects is huge, always, and actually easy to fix as well. And then maybe you do not have enough work for each thread. You have load imbalance among threads. And then when you do MPI communication, maybe your other threads are idling. And last one is like sometimes you want more optimized compilers and libraries for threading. And we tell users if a routine does not scale well, what we want to try to check, examining your serial section, the critical section, to eliminate those, and to also to reduce the number of OpenMP parallel regions to reduce overhead. And we talk about loop collapse, loop fusion, permutation, things like that, and add no weight. And for load imbalance, you can try different scheduling options. Dynamic is a good one. And the other one is for OpenMP scaling, you want to, like I mentioned, try to find your MPI, the sweet spot for the combination. And the easiest one I always try to emphasize is to test different process and thread affinity options. It's actually a low-hanging fruit, easy to get. then to modify your algorithm to achieve some kind of performance. So I have an improving OpenMP scaling webpage to help users to go through some of the steps, and some case studies are there as well. So now I'm going to talk about case studies. Lots of users provide me their. Basically, it's some of the applications that touched upon the aspects I mentioned. So this is NPB hybrid MPI OpenMP. So first, what you notice that the thin line on the top is the memory footprint. When you increase number of threads, OpenMP hybrid MPI OpenMP helps to reduce memory footprint on the node. And these two plots are quite busy. The left is one the NPB BT benchmark, and the right-hand side is the LU benchmark. And different colors represent different compilers. So one suggestion is try different compilers for your application. And so the different number of threads, and then you would try to find what's your sweet spot. So for the first one, you can, so for the first one, actually, OpenMP does not help significantly. And second one, and the sweet spot is at 6 threads. So this is another application, FVCam. Basically, it has different components, and different components will behave differently, even in your same application. And so one thing to notice is that from 1 thread to 3 threads, you would see that performance suffers only very small, but then memory footprint reduced to half. So this is a trade-off you would like to take, actually. And this is another application. The story here is basically to add OpenMP incrementally. There are 4 hotspots sections in this code. The collision is the biggest. It takes about 95% of time. So you add OpenMP to it, and then you get down about 60 times speed up for collision. Then at that point, stream, the next hotspot becomes huge, and you would like to add OpenMP to that, and then you reduce another 89% of speed up. And then from step 2 to step 3 is the adding vectorization.
This is on Xeon 5.
Yes, Xeon 5. And the right side, basically, I would like to ask people to try different OpenMP affinity choices. For the Intel, you have balanced, scatter, and compact. Normally, we see that balance is the best, but sometimes scatter is best as well. So try that. So this is an example of overlap communication and computation. As I illustrate on the right side, it's very hard to do. You have to know that you have to know what part can be separated out for communication while you're doing your computation. It needs a higher level of MPI thread support. All the compilers we have on our system support that to do the overlap. No. But you can put into.
The reason it's not common is almost none of the runtime, none of the MPI runtime do a good job.
Right.
So people tried it, it didn't work, pull it out. Tried it again, it doesn't work.
We're working very hard on that.
But if you wanted the overlap, you have to put it inside. Otherwise, we tell users just do the test. Even if it's inside, we tell people just do the master to do the communication.
Right, but I'm saying that you could use, one thread could do ISIN, and then all the threads could do compute, and then,
Yeah, it's not as safe to do so, yes. So these.
That means you have to go out, or you do a master.
Yeah. So this is the performance results from, you can hybrid C and D are the overlap result. So this is application of the Ocean model, next generation Ocean model. And they basically explore different things. Like they explored OpenMP tasking because it's unstructured mesh, and it's like sort of naturally in a tasking way. So they tried this, and and with their block concept. And then they also try with element in their algorithm. They can use the loop level of parallelism, just add OpenMP directives on the bottom, or they can do like pre-compute, where's my loop boundary. It's called single program multiple data method. And basically they compared all three of them and found out loop level is the performs best, and it's also easiest to do. So they will stick on that. And the next step would like to explore nested OpenMP. So that's the comparison of these. And then they also compare different scheduling on the left side, static, dynamic, guided, and found out basically static is the best. Then they add on to SIMDI. SIMDI helps a little bit, so they decided to stick on with static SIMDI of OMP. On the right-hand side, after you stick onto static SIMDI OpenMP, they tried different combinations of MPI Tasks and OpenMP threads. So they found out their sweet spot becomes 2 times 12. So this is what they get. And this plot is, so the previous plot you can see is up to 3,000 cores. And now with this fixed sweet spot, everything they found, they start to scale up to much higher. And you can see that flat MPI can only run up to 12K. And then in this case, they actually tried different combinations of MPI Tasks and OpenMP, and they found out another sweet spot. 8 times 3 is the best. So always try, these things are easy to try and always get you actually quick turnaround results, right?
Do you know what's going on with the red?
What color?
I mean, what happens when it is literally just jumping around?
Yeah. 12K is the best. I don't exactly know. Could be, yeah, problems.
So many cores.
Problem size. But the lessons learned is try these, and it's easier than modify your code. So this is another example, application, box lib. So in the middle bottom, you can see it's the AMR, so you have different levels of boxes. All these boxes, you have more and more levels to try to finer your resolution. But the traditional way is out of these boxes, they assign them to the different MPI tasks. And then underneath MPI tasks, you would use OpenMP. The problem with it is it causes huge loading balance, this original way. And in your code example, you would see lots of different small sections of parallel do, another parallel do, another and parallel do, like that. So this is basically the fine-grained OpenMP. So they did some revolution work with trying to do called tiling threading model. What they do is for each box, they make distribute box as little tiles, and they put tile as the outermost loop. And within each, then for each tile, you would do, then you have your MPI and OpenMP in it. Oh, no, sorry. MPI is already still outside, sorry. Hmm? Yeah. I think my private should be a J, right? At least there's a typo here. Mm-hmm. Yeah. Okay. Yeah. No, I haven't tried. It's the users supplied. Basically, the story there is they have lots of sections of fine-grained OpenMP and then threads, creation, destroy, things like that. So with the tiles, you put tiles outside, and it has much better load balance. Also, and because each tile you can tune them with the small size, and the tile would you have a good memory cache reuse. So this is their scaling result. This is also on the Babbage system, and it basically scales up to 120 threads. Okay. So this is a strong scaling box lib data, and with compared to MPI, I'm sorry, it's a weak scaling, sorry. Then with MPI, you add different number of threads. So MPI plus 12 OpenMP threads is the best on this is on the Edison system. 12 threads is so how many you have in the NUMA domain, the best. Okay, down to another application. So this is just an interesting story with the Heap Erase compiler flag. So we have a kernel code. We have Cray compiler optimized and Intel compiler optimized. At some point, they're comparable, and then we did some vectorization work. Suddenly, Intel compiler version is 6 times slower, and had some investigation, and turned out it was this flag. The flag, what it does is put the automatic arrays and things onto heap instead of stack. So the story is because the private copies on the stack is so expensive, so it's slower. So there are two ways to get performance back. One is just remove this flag, and then in this case, once you remove, you put everything back on the stack, so you want to increase OMP stack size. And another alternative is use thread private, so you have thread private copies on heap.
So I can comment on this a little bit. I think this is a bug in Intel's compiler. It's not because allocation is so expensive, it's because there's a lock in there. So all the threads compete for the lock. And we could do a much better job with that. That's one of the things I'm working on.
Okay.
But in general, yeah, if you use Heap Erase, you're going to, inside parallel mode, you'll get a lock, and you'll get scale.
So basically, on your heap, you have to maintain thread private copies, right?
Yes, exactly. Slower than stack. But apparently, a lot of people just automatically use Heap Erase because they don't understand the stack size files. So it's kind of a combination of we're not doing a great job, and our messaging isn't so good, and customers don't really understand how to deal with deploying the stack.
Where's the lock with allocation procedures?
I'm not going to comment on that. It's more complicated than that.
My suggestion actually was to look at the allocation.
Right, well, so it's actually
Okay.
mostly in the Fortran RTL rather than now.
That's what my suggestion.
Yeah,
The allocation
but it's
But this is,
But it's-
we're working on trying to do.
so the story. It's in the Fortran code, so at least
Right,
you
right.
would want to have you want to use runtime
But the
allocation.
question was, is it really the Fortran allocation, down inside the allocator, or is it actually deeper down inside libc?
Right.
But even we fix that, we still have some slowdown versus going to the stack.
Right.
Stack is going to
You always have to maintain private copies, either which way.
If the size, you don't have stack overflow issue, right?
Correct. But you could call allocate yourself. The user could call allocate, and then that would be something we like.
So there was an early problem found that people have allocation memory inside their parallel regions that slows down. That was a bug fixed, right?
It's
Yeah.
fixed, but
Right.
not in all cases.
Okay.
It's unfortunately complicated. It shouldn't
Sure.
be so complicated, but it is.
So this team also explored nested OpenMP.
Now, does Cray have a problem with that one? Did you
Cray doesn't use this flag.
Well, but so if
Cray-
you took that same code and compiled it with Cray, you wouldn't have the problem.
No.
Okay.
Yeah.
Well, we can take that offline.
So, yeah, I'll carry on with more on this code. They tried nested OpenMP. So far, it's a little bit slower nested OpenMP compared with one level. And I'll ask them to try KMP hot teams, and hopefully we can get this faster. So one of the things they learn is basically, because we tell them to use OMP num threads, and they only use a small section of their codes with nested OpenMP. All the other, many other regions, they use the default number, the one level OpenMP. So I tell them, to do that, basically, you would don't use OMP num threads equals 6, 4. Put that into a num threads clause in the nested parallel region, and then leave the OMP. You can use OMP number threads environment variable for the other regions, so that's more flexible and simple. That's a long. This next few slides are a long story of the NWCam OpenMP optimization. They did a lot of ways of optimization. The first slide shows in this algorithm the baseline OpenMP performance. So there are basically two hot regions, loop nest and the get block. The get block doesn't scale at all, and loop nest does. So this is what you have at the baseline. So the next slide, they start to optimize the get block. Let me show you. Yeah, so get block, it's still not scaling well, but much, much faster compared to the first one. And they did lots of things like parallelization parallelize the sort algorithm, loop unrolling, and memory alignment, and loop reordering. They have lots of things. It gives compiler some hints, and this is a speed up. This is like all these algorithm things you can do. And also the loop nests, I think compared to the first one, there's also optimization on the performance improvement there. So this is one work. And then NWCam, another kernel, what they do, they have 3 ways of OpenMP. They did 3 different OpenMP optimization. The first optimization is with the loop level. So this algorithm is so memory intensive that it can only run up to 60 MPI tasks. And then so on top of that, they start to use add on 1 OpenMP or 2 or 3 or 4 for this OpenMP optimization, the loop level. And I didn't show the second way, but the third way of optimization is they explore tasking. So they try to find out how task could work for this algorithm, and they use basically the master task to assign work. And then there's some local conflicts they did at the end to do local reduction. Optimization 2 and 3 was tasking. You can do pure OpenMP now. But the first one, the loop level, is the 60 MPI tasks times plus different number of OpenMP threads. And tasking is best in this case, the blue line, and it scales all the way to 240 threads. So, and the story is also that everything you do on the Xeon 5 and you bring back to the Xeon, it also gets speed up. You can see it on the right-hand side. So and the overall speed up, I think they got 1.3 times faster than pure MPI for this code. And so I showed you about the 4 lines of finding out sweet spots. This is another way of showing sweet spots at a sort of heat map, and you can see different colors. So each horizontal line is now a different, a constant number of MPI times OpenMP. I think I can't go through this. Another NWCam work by another team. What they have is the matrix and multiplication. MPI A times B equals C, and 1 horizontal times 1 vertical equals C. So they what they invented is basically they distribute the matrix at the thread level, and they call them blocks. So you can assign teams of blocks, say on this T1, T2, T3, and then you get the sub-blocks of the results, and then you put them together. But then for each thread, you can assign teams of threads, and underneath that, you would have, basically it becomes nested OpenMP. So you have, say, 6 teams, 10 MPI with 6 teams. of 4 threads, and these 4 threads are done by an MKL. So you can do a nested MKL underneath it. So by default, MKL dynamics is true. Then basically you would set within an OpenMP region, the number of threads is 1 for MKL. So in order to enable MKL with multiple threads, you want to set it to false at the end. And then you get very easily usable nested OpenMP with MKL. I think I showed results in this case. The right-hand side is basically a heat map of each little block is a different configuration of their test cases. So for each test cases, they compare to different algorithms. And with the newer reduced algorithm, the more red, yellowish color is better. So that's the improvement they see. I'll skip the slide. Basically, it shows OMG Tag Device works, which is good to know. And it's portable, but it's not we're going to use on Babbage. All right, I mentioned I want to tell you about declare SIMDI, how this is useful. So this is a prototype of the climate code kernel. It's very complicated. It's called function, and that's called function A. The function A is an elemental function. And then inside it, you call different B and C, and all the way down different. So the vectorize report shows I can't inline, I can't vectorize things. So what we did is, you add attribute force inline and add declare SIMD for this function, and now it's vectorized. So another thing we did is instead of vector aligned directives, we added in OpenMP SIMDI aligned. So SIMDI aligned, as we said, it could be dangerous. And however, we try to push more towards portability, so we want to use SIMDI aligned. So for the SIMDI aligned, what we found out is that if you just put SIMDI without aligned clause, without putting into the specific arrays that are aligned, and you don't see that 8% performance gain. So this is, for this kernel, basically every single digit of performance gain is useful. There's a very, very little things add together get the performance gain. So 8% to them is big.
That should be much better on KM, shouldn't have to. Because if it does an unaligned load to aligned data, it will be the same speed. So as long as you align your data, you don't have to go.
That's what we were trying to get, yeah. So the compiler, we would hope the compiler should know. So for this is just a kernel, and there are like 48 loops, and each of them has 10 plus. It's very hard to do so. They don't like to do it, but so what?
Right, and saying the data is already aligned, then it will be the same speed. That's true. If it's not aligned, then it will still be slow. So if you
But it's still better than NC with unpacked.
which is correct. Yes, exactly. So what I'm
this is
saying
what I'm
is
saying.
that this dir attributes align 64 or decal spec aligned is all you should need to do.
That's.
You should not have to go through an annotate.
I would hope so, yeah. So basically, I think as long as you're in the scope, you're not into a separate subroutine, that the compiler does not know your scope anymore. If it's no, you should not.
Because the hardware, as long as the data is, when it actually does the load, as long as the data
Yeah.
is aligned, it will run at full speed.
Or yeah, either you would align it or use like you said, with flag, everything is already aligned. Why do you need that, right? But in this case, we actually, in the table you can see, we do have the align 64 byte in it, but the compiler still, with the aligned, still helps. So
That's because that's for cadence zero.
yes, that's okay.
That shouldn't be, on KNL you shouldn't.
Okay, and then so we were also talking to the Fortran standard, because for C you have a you can declare it's aligned. So if
That's not part of the C standard.
it's
It's an extension.
sorry, but you have a way to do that. But for Fortran, I wish either you could align it in your declaration, or you have some kind of equivalent of compiler flag.
We have the same problem with allocating arrays.
That's yeah.
Right.
So here's a somebody's Srinath test SIMDI suite. It's a Python script to test all these OMP, declare SIMD, different things, and how it could get as close to AVX performance. So first things we found out that align is really important. So otherwise you get way off performance. But still, nothing can be compared to the native XAVX flag. Yeah.
So for the Intel compiler 16 nano, because this is compiler of OpenMP standard, right? We added this processor clause as part of the class as the Intel's extension. So once you put the processor, the core and display DX, whatever the name I can use, you'll get a serial form flag.
But I think for compilers, without OpenMP at all, you would already tell people to use XAVS in your compiler flag anyway, right? So we would just try to use it without it and compare.
Well, then you're getting SSE code. So.
Mm-hmm.
Can I just ask, have you tried, for example, meantime optimization? You know, because at least the latest version should be able to propagate alignment from the declarations or even the allocation size to the users, even across compilation modules. So this might not.
Thank you.
Without any need for any special market.
Then why would we need an aligned clause?
It works, it is language independent. So it takes the alignment information from either the declaration, and then as you pass it, you know, I suppose the problem is that when you hit a function, when you get an array and you know how aligned it is. As a parameter, this is basically being propagated as you can propagate constants procedurally. The newest GCC also propagates alignment.
Yeah, that's.
So maybe it should be able to just use the right thing for without the need.
This is what we do, yeah. So that's our goal. Users don't want to specify this. I think for private and shared, you have to, but for alignment, we try not to have this burden. Okay, there's also a thing I asked in the committee. So there's aligned, there's a restriction. The type of list appeared in the aligned class has to be C pointer or Cray pointer, or it's a allocatable attribute. So C and C++ allows arrays. Why would Fortran have such a restriction? Can we relax it? So we have two compilers we tried. One of them conformed to it, it won't compile. The other one compiles and does C speed up. Intel, yeah, speed up. Yeah, I asked that. It exists in OpenMP3. Yeah. So this is just one last slide about what users like to have. So we would like to have threaded libraries. MKL is part of Intel runtime and MPI, Intel MPI, Intel OpenMP, Intel MKL, everything is so good together. But then if you mix different OpenMPI with different OpenMP for different, then how do I know what thread I want to use for my libraries? So within a parallel region, you call PETC, you want to call single threaded. But then users also want sort of way of, I want multiple multi-thread PETC, for example.
So there's a difference between threads saved and
Threads.
threads. Threaded means that the library uses threads to improve things somehow.
Okay.
Thread saved just means you can call them from multiple times without doing it. I'm not Which one are you asking?
Both.
Okay. Most libraries, system libraries are thread safe.
Thread safe, yes. Even MPI is thread safe. But then for MKL, so for like PETC, for example, like MKL has both, right? And
MKL uses threads and is also thread safe.
yeah.
Although, as you know, you have to be careful not to get too many threads, which you've already covered.
But then also for multi-thread, whether you want a single thread and a multi-thread different API version, or you want if I am a library developer, should I always inquire at OpenMP runtime to know whether I may pair region or not? If it's a good idea to do that, but on the other hand, you have to always add OpenMP function calls, library interface into your code, and you have to always compile with flags to be able to runtime aware of OpenMP. How to do that?
Back to what James was talking about, composability. OpenMP doesn't
Yeah. So another thing users normally like is one consistent behaviors among all compilers or different vendors. These are two examples, like max active levels. This is for nested OpenMP. It's different right now. Some compilers is set to 1, so you didn't get nested OpenMP. Another example is default number of threads. We had lots of discussion on that. I think probably it's dead already, but so right now the decision is do ask users to always set that in explicitly. But if we can have some kind of consistent behaviors, like if we can define what is the max number of threads being, whether it's time of cores times number of cores times hardware threads, and also it has to know what has to be MPI aware. So it's very hard. It easily cause oversubscription. But things just along this line, consistent behavior is what users like. So my summary is OpenMP is fun and powerful, and we recommend users to use hybrid MPI OpenMP. We always keep portability in mind, and we'll keep promoting and working with users on using OpenMP more. Thank you. Sorry.
When I came in, I saw a slide that says SIMDI, and it says at the bottom there's a problem. Did I just read that wrong?
SIMDI, which one?
OpenMP SIMDI.
Aligned.
All the way back. That's my
Oh, I see. There was a section on OpenMP SIMDI. I know what you mean. This one.
warning. Incorrectly.
Sure, that's just ignore the sentence.
Yeah, basically it says because the compiler ignores the timings, right?
Mm-hmm.
So if the loop has loop carry backward, then you get this, right? This is nothing new versus the ending kernel.
Kernel 4 has the same problem.
Yeah.
Yeah.
So I have another slide there about here. So here is I compare SIMDI aligned and vector aligned. That's different, right?
This is a word.
Yeah, I know. I would just compare for the second one is not forced compiler to vectorize, but the SIMDI is.
I have a question. So early on, you showed how many workloads were threaded and how many threads they were using, and you later then said that you recommend at least one MPI at least one MPI rank per unit. Right?
Oh yeah,
so
yeah.
That's the
First touch when I mentioned
that.
that.
Had a couple of applications that were using 48 threads. So do they not have MPI at all? Because you can't use 48.
48 thread is actually no MPI.
No MPI.
Right.
And they were trying to use the whole machine.
Yeah. Cray. That's Cray's application launcher.
So to find background is just the gray batch system where you'll find launching something not allowed to use. But it also does Affinity. It does a ton of stuff, yeah, but if you use MPI run, which is available, you may try and use it. You know, you actually can't get on. You just can't get for a product. That run launches spread well and keep it on there. It gets upset with the extra. That's the Affinity system, yeah. Ray has an internal workaround for it. Yeah, we know. And then that's what the dash S was. Actually, there's another workaround. Okay. We use in our libraries. We actually in the Ray used extra threads in its MPI library and other libraries, but because it had internal ways it stopped doing Affinity from when I create my thread. Back on. That's accurate.
Okay. Ask you more about it. Thank you.
I have a question for you. Have you tried Create Tools' ability to tell you where to place your MPI records?
Create tools.
So the Create Tools will monitor your MPI program, look at the memory passing the footprint, and then it will give you a file that says this is the way you should lay out.
Oh yeah, the rank reorder file. Yeah, we use that a lot. Even the perf tools tell you at the end.